might go out. Like, I didn't think it was going out. Starts jogging to first base. It's right down the right field line. Gets to first base, hits off the wall, and he had no chance at second. And it hits him off. And then in the ninth, he hit a home run to like bring it within one, I think. And then he ended up pissing off the other team because they just like slow trotted around bases while losing. And so now he basically has his whole team hating their whole team.
I did that before. Like, I had full classes in these notebooks. So. But then I didn't. So.
I gotta say, the Cardinals.
It's kind of nice. I have like my stat notebook and then my psych notebook.
Probably most underrated player in baseball. If you look at what he's done like the last 5 years. He's
I
so
always love
consistent.
him.
Yeah.
He's my
He's
favorite.
still kicking. How old is he
Is it pretty?
High 30s,
now?
at least.
The audience, I think, something that's like the rest of the yesterday, like 260.
Yeah.
So that's
I
a
love
week.
him.
Oh, so that's next. Wait, but it says nowhere, no.
And then the Nats lost. I somehow want the Nats to win the loss.
It's for our team.
I know it's not gonna
Because
happen.
I'm like, I can't miss classes due
Not next week, but the week after.
the Wednesday.
I want to see Minnesota beat New York
Yeah, you can't.
so badly.
And baseball.
Send that Friday.
I think they could. Their offense is. Yeah.
Okay. So nice to see you before the break. For schedule, in the course, of course, Monday and Tuesday are college break, so we won't be here, won't have any office hours. On Wednesday, we'll continue talking about multiple regression. And then I won't be here on the 11th because there's an event at University of Vermont for Vermont Genetics Network and its research activities that includes research opportunities for undergraduates. So I hope to get involved with that, and do that I have to be at the meeting. So I'll be there. I encourage you to go to the Pi Mu Epsilon talk later that afternoon, or look at the integrity recording or the integrity recording of the student seminars from earlier in the semester if you didn't see those. And then so the week after that, we'll continue with some of the diagnostic information on multiple regression. I'll get a homework posted sometime either on this weekend or early in that week that will be due over here that will cover kind of a multiple regression assignment. So there's kind of a little bit of less to do, a little more reading to digest for the chapters over that time period. And particularly this week, and starting this week, I'll shift my office hours down to be Monday, Wednesday, Thursday. They've been kind of officially Monday, Tuesday, Friday, Monday, Tuesday before the Wednesday assignment. Now they'll be Monday, Wednesday, Thursday. So the Tuesday, Thursday thing is just going to be a little shift. And I'll just update that on the website so that I have a concentration of office hours before homework's due on Fridays. But as always, individual times can be arranged. You can write if those times don't work, but mostly I do it, around plus or minus the different classes, and then I'm here on Thursdays. So I'll be here starting on Thursdays to do things, right? But today we'll talk about multiple regression, right? How do we get multiple things, multiple x's to predict an outcome? So we'll go through some formulas, then do an example, and get a good start on looking at this stuff. Right? So the model for multiple regression, it's called multiple linear regression because the predictors, in whatever form we put them, end up being linear function of the coefficients. The average response for y given a vector of x variables, and this little tilde is going to be shorthand for my set of possible predictor values, is going to be there's going to be intercept plus coefficients times each one of these possible predictors. And so that's the average y, right, or expected value of y. And another notation, it might be e of y given our x's. Right? And then the y values that we see are be the mean function at this x being a particular values xi plus some error. And so this here means x1 is x1i, x2 is x2i, dot dot dot, x of p minus 1 is the x of p minus 1 for case I. So it's the particular values for person number I. And these EIs are distributed normally with a constant variance sigma squared, and they're all independent of one another. So that becomes our model. We have this kind of average response that depends on all the coefficients. We take all the different x values for one person on different variables and plug them in there. It'll give you an average, and so then the response is thought of as that average plus some random vertical distance. Right? So this is very, very flexible. God, it's carpeted. That it's very, very flexible in what it can do. Right? You could just simply have two variables in there with a different slope. Right? Second cup of coffee. So so just as some examples, right? So if you have x1 and x2, if it's two variables, you'd have beta 0 plus beta 1 x1 plus beta 2 x2. The data you would see for people, you'd see their y value, and you'd see their value on x1, and you'd see the value on x2. And so different values x1, x2 can combine to give this. You can try and draw a picture of what this looks like. Right? And this is supposed to be 3 dimensions, so here's x1, and here's x2. And you would have some point out here in the plane. Let's put a point here at x1, x2. And this dimension is y up here. Well, the average value is some vertical, maybe I'll make vertical going red here. There's some vertical distance up here. And this thing, if you would map it back kind of to over that distance, it should be up kind of about up to here. There would be the mean of y given the x1 and x2, right? Kind of out here. And what this thing has, you know, if it were just one variable, it would just have a slope in the x1 direction. And if it were x2, it would just have a slope in the x2 direction. But since it has x1 and x2, it's really a plane. It's some type of, you know, piece of paper, or kind of, you know, a plane kind of put on there. It's kind of hard to draw. You don't do it with this color. So you have some kind of plane up here, and this thing is actually kind of intersects with that plane. And so as x1 and x2 change, the values of y are going up, and like that. Right? It's kind of hard to draw, but anyway, it has the two slopes. So if you tell me both x1 and x2, then I can tell you where the average value is. And it's either one changes or they both change, you get another value projected on there. Right? That's kind of the basic one, but you could have mean functions where there's just one x essentially, but you use it in multiple ways. Right? So you could have a beta 0, beta 1, x1, beta 2, x1, and squared can be a variable. So you can model things that are quadratic with the one variable, and it becomes linear in the coefficients, but even though it's not linear in the x value that's there. So you can get quadratics, you can put in third order, fourth order, if you have a lot of data, and you really, if that's really the kind of the situation. Third order, fourth order can be quite a good approximation to something that kind of levels off, or something that doesn't do anything for a while and then takes off. So it can mimic quite a few things that are possible. It can have, if you have two variables, you can have an interaction. And so this way, we just have an effect of x1, effect of x2, but maybe x1 and x2 have some synergy or cancel each other out to some degree, and so you could have an x1 times x2. You can have an interaction here. Now, very explicitly, the effect of changing x1 is not just to change the response by beta 1 times x1, but you change x1, and there's a change over here that depends on what x2 was. Right? So it can be a little bit more complex. Right? So squares, interactions, multiple variables. You can also have indicator variables. And I'll just put an I here for an indicator. So I is going to be 1 if yes, 0 if no. That would just be kind of one coding of something to indicate a group. Right? Instead of being yes to some response, maybe it's group 1, and the other one is group 2. But it's just kind of a dummy indicator variable. That indicates the presence of something, presence of a disease condition, membership in a group, or some response. And then you can have beta 0 plus beta 1 x1 plus beta 2 times this indicator. Right? This plot, if x1 is continuous, and you have, you could plot y versus x1. And now the expected value of y for a given value of x1 will depend on whether it's in that first group or not, whether it's yes or no. Right? And so if it's yes, or if it's no, right, and that's 0, it's effectively just beta 0 plus beta 1 x1. But if that is yes, and this is a 1, you get this extra intercept, right? So you get a shift. And if beta 2 is positive, you'll get beta 0 plus beta 2 plus beta 1 x1. So you get these parallel lines, regressions. And one group would tend to have points, scatter plot points, around this one. You know, they can't overlap to the other group. And the second group, if this is that line, would tend to have points that would be centered around that one with some variability. And of course, the groups can overlap. But to the degree that the groups are separated, this coefficient is going to be, kind of important in there. Right? So you can do shifts. One other model that is used is called the analysis of covariance model. That has an interaction, but then has an indicator, but then does an interaction with that one. Right? What does that model enable you to do? So we have an x1. And we have an indicator. And if this was voice activated, then I could just say small pin, and I wouldn't have to click. Beta 3, that's the next innovation, right? So that would have an interaction and this indicator variable in there. What would the mean function plot look like for this thing? Right? We have x1 and we have y. If I equals 0, right, then the average is just beta 1 plus beta 0 plus beta 1 xy. Right? But if it's I equals 1, right, then this is 1 here, so we get the beta 0 plus beta 2. And with I equal 1, well, we get that times x1, but we also get this times x1. Right? So then we'll have beta 1 plus beta 3 times x1. So you can get two different slopes, right? And so if the groups are going up in different rates, that could be useful for modeling them. The groups will be kind of together here, but maybe separate a little bit later. So you might not have much of a difference up here, but you have more of a difference up here in the groups, right? So you can get the groups that are separating, but kind of starting similar. So it's pretty flexible. You can combine these things. So you could get a quadratic going off for one or going down. This model is sometimes called analysis of covariance. So you can really imagine a lot of different things that are there. We can do estimations for these things given our data. The data values that we'll have, level y for each individual, and then we have, I guess I wrote 1i, x, 2i, x, 3i, up to x, p minus 1i. These are the data for all of our individuals. Everybody has their y's and all the x's observed together. Okay. To do estimation of the betas, we can use the least squares criterion like we did with simple regression. We have some function, call it q. We can look at the difference between the y's and the prediction on the line, the projection on the line. And some of those are positives, some are negatives. We square all those, so it's called least squares if we have that criterion. Right? So we're going to choose the betas to minimize the sum of squared deviations. Right? So instead of just a plot where we have, these vertical distances around this, here's y, oh, sorry, that's an x, and that's a y. So in one dimension, it was like this. Now we have this plane, and the points are up above or down below that plane, and they're all being projected to there. And we can tilt the plane this way, or we can tilt it that way, or we can move it up and down. And then that generalizes to p dimensions, right, or p minus 1 dimensions. So it's not something we can visualize, but there's kind of this hyperplane, and we're projecting the y's, and we can adjust that projection to make it as small as possible. So we can solve this thing. So if we take a partial derivatives of q with respect to each of the betas and set that equal to 0, we end up with p equations because we take that partial derivative. We're not going to do it explicitly, but there's p different coefficients there. There's p equations, p coefficients. So you can solve these different equations for all the betas, and you end up with solutions. And we're going to call those the estimates, right, for all those. Right? The details of doing that are in the Statistics 351 or in textbooks that would talk about linear regression, linear models in detail. The easiest way to represent all of this is with linear algebra and matrices, and it's a little compact solution once you do it that way. But given those estimates that will come from the computer, the predicted value or calling it the estimated mean, where is the estimated average, is going to be our estimated intercept plus our estimated slopes times their times the data, p minus 1. So we get the estimated slopes, we get the data values for everybody's x's, and that gives us a prediction for everyone. The errors or residuals for case I is the y value minus its predicted value, just as before, where the predicted values now is from that longer, bigger equation. And we can estimate as well sigma squared. The estimated variance is going to be the sum of the yi minus the yi hat squared, and we're going to divide by n minus p, which is the number of coefficients. This is also the sum of the residual squared over n minus p. And this choice is done for statistical theory purposes. You could divide by n or other things. Maximum likelihood estimates would divide by n, so it's not necessarily the only choice, but under the normal model, oops. Oh, there we go. Under the assumptions under the normal linear regression model, it turns out that the expected value of the sigma hat squared is sigma squared, and the expected value, the average value in repeated samples of the slope estimates are the slope and includes the intercept. So they're all unbiased, and so that works well, and it's desirable. And we also, under that error model and the normality, then can do inference for the different coefficients. Right? So we get those on average. We're going to use that estimates there. Inference for our parameters. If we wanted to test whether one of the betas is 0 versus not, we can divide the estimated coefficient, that comes out of the least squares, by an estimated standard error. Again, the statistics 351 goes through the formulas for getting all that. And this is a statistic. This is something we calculate from our data. And so under the null hypothesis, this t statistic turns out to be distributed as a t distribution, now with n minus p degrees of freedom. Simple regression, it was n minus 2, because there's the intercept and one slope. So p minus 1 was 1, so p is 2. Two coefficients. And so if the null hypothesis is true, these t distributions are all centered at 0, so we expect beta hat to be pretty close to 0 relative to its standard error. So we'll reject the null hypothesis. Reject the null hypothesis if the absolute value of the t statistic is greater than the 0.975 percentile. Right? If we do reject, we conclude that the coefficient is statistically significantly different from 0. It's kind of a mouthful to say or write. Right? So this, and conclude beta j hat is statistically significantly different from 0. Some people might just say that it's significant or it's statistical or statistically significant, but we're concluding that it's not 0, and therefore there is a meaningful slope and there is some relationship with that x to the outcome. You can also test this intercept, right? Is the intercept 0 or not, right? Often we keep the intercept in there even if it's not significant, just because it helps fit the data. It might not be the main purpose, but it's not using up too many degrees of freedom, it's not too much to estimate. So usually it's there unless there's a specific biological or fundamental reason why you wouldn't have an intercept, and you have to go through 0, 0, 0, 0, 0, right? When all the x's are 0, y is 0. Otherwise, it just kind of helps it fit the data. And most of the x's are somewhere away from 0 anyway, so we're not too concerned with that. You could test it. The other thing we do, right, before you test any of these individual ones, there's usually a test that is there any difference? Just like an analysis of variance, we usually test, is any group different? And then once it's different, we go in to look at which group is different with contrast and things like that. Right? So there is an overall F-test. In regression. The null hypothesis in this case is all the slopes are 0, right? That none of the x's you're proposing are significant predictors of the y, right? And then the alternative is that some beta j from this set is not equal to 0. Usually, in analysis of a regression, you start with something meaningful as a predictor. You know something about the problem, unless you're completely searching through a new area and you don't have any idea of whether there's something. So usually you start with at least something that's significant. And then you're testing in multiple regression, are other things also useful? Or can you do better than just doing your best variable? Can these new variables also help you? So usually this is not the most interesting test. But to test this one, we create an ANOVA table. So in this, there's a sum of squares for regression, or those, sometimes this could be called sum of squares for the model, and it's a sum of the predictions minus the overall average squared. Same formula as simple regression. But if our predictions are making a difference, then the y-hats are changing a lot, right, as you change the different x's. And the y-hats differ from the y-bar, so there's a big contribution there. The sum of squares for residual. Other programs might call it sum of squares error. And it's the sum of the yi's minus the predicted values. Right? And so again, yeah, if we do very good prediction, then this is small. If the y's are kind of scattered about, not associated with a line, then this is bigger. Right? And sum of squares total is the sum of those two things, and it's the sum of the y's in comparison to the y average. Right? And it turns out these things add up. You square out both of those things, and some things cancel, and it regroup, and it ends up being that. Right? There's degrees of freedom associated with each of these things. Right? There are p minus 1 degrees of freedom associated with the regression. Right? So there's p coefficients, but you got to have at least an average to describe your data. So p minus 1. The residuals, there's n minus p. In linear algebra or geometry, there's kind of n-dimensional space because they're n points, and you're restricting it to a plane defined by p coefficients. So you're projecting onto that, and that's what's left over. Right? And n minus 1 is those add up. Right? And so if you divide the sum of squares by the degrees of freedom, you get a mean square. And if you take a ratio of mean squares, you get an f, and that's the statistic. Right? And so if this is big relative to this, adjusting for the degrees of freedom. So if the regression in particular is making a difference, and in at least one dimension, it'll be significant. Usually that's significant, and then you go and look at individual coefficients. If you're totally searching and nothing shows up as significant, well, then you're need to kind of re-examine the purpose of using regression. You can't find anything at all. So the ANOVA table, right, has regression, error or residual, and total. Degrees of freedom is p minus 1, n minus p, and n minus 1. The sum of squares, the sum of squares for regression, sum of squares residual, I'll use the R, and sum of squares total, they add up. There's mean square, which is just the ratio. I'll just write mean square regression, and mean square error gets calculated there. And so a mean square is a sum of squares over a degree of freedom. You could do this just ordinary estimate of the variance of y's, but they don't add up, and we usually aren't using that estimate for anything. And then our F statistic we calculate is the mean square regression over the mean square error. And under the null hypothesis, this F statistic is generated, is distributed as an F distribution. And then the degrees of freedom come from the estimate of variability that's going on there, right? So the p minus 1 and n minus p. So if that F statistic is big in comparison to this distribution, that means that the sum of squares error is relatively big, bigger than you'd expect under the null hypothesis, and you reject it. So you reject that. Reject h sub 0, and this is the one where all the coefficients, all the slopes, if the F statistic is greater than the F distribution at its 95th percentile. And this is just a one-sided test because everything's squared, so everything is positive if there's a big deviation, right? Out of the, so that's the, so usually you would make a note that overall there is some significance, and then look at the individual coefficients, right? The other thing that comes out of the ANOVA table is R squared and residual, an estimate of the mean square error. But we'll revisit that as we talk about things. I wanted to look at just one quick example of things in multiple regression. So I went back to this Nebraska County data set. So we have it in there. Those are the names. I added in a variable. There's a FIPS codes are codes used by the federal government to enumerate states and counties and places. And so every county has its own FIPS code. And so the FIPS code for Nebraska, the FIPS codes are 31 is the state code for Nebraska. And then they're 1, 3, 5, 7, and so on. There's 93, so we'll go to 180 something. So another thing that is in the data set was this that I grabbed from there was whether they had a website for their county fair, right? I assume all the counties that have their own county fair have that. And so some of them are, they're not missing, they're just blanks that are in there. So I can say, if it's blank as dot numeric, if it's not blank, let's do that. If it's not blank, right? So now these numbers would be switched. So I'm switching this, right? So it's a 1 means that there is a county fair, right? To have a county fair, maybe that's related to population size. So they have to have a certain population size to run one of those things and bring in rides, and bring in animals and all that. We can think about other variables. So we have population density, right? We have area, but maybe that's not key to getting the population size. So we can divide the population by the area and get a density measure. I was going to try to get latitude, longitude, but the permissions have all changed And there used to be a command where you could just type in like a county or some information and get that. But now you need an API key from Google Maps, and there's a registration process, and I didn't realize that when I was trying to do it. So I was hoping to do latitude, longitude as another variable. But what I really want to do is distance to the Platte River, right? Because the pioneers went along the Platte River, going out to Colorado and Utah, and established cities along there. So all the big cities are along the Platte River, and that's Interstate 80 going across there. So if I can get distance from the county center, say, to that, it might be relevant. But that's something else for later. So let's look at predicting population. Right? Last time, we figured log area versus census was not statistically significant. But now let's just add another variable in there and see what happens. Let's put in the county fair indicator. Right? So here's the output that comes out of that. An intercept, log fair, log of area, and then fair. And so I don't have that copied over onto this, right? So 10.6, let's see, can I arrange this so I can see that and write? I've been able to do that in the past. Let's see, can I make it? One of these should be, that's not, okay, now I can make it smaller. Something like that. And if I can grab this edge there, you can push this over here. Not too far. And make this one smaller. And put this thing down here. What it does is it makes things a little funny, right? So I wanted to read, so if I could get rid of that would be nice. So the predicted value on the log scale, here is this intercept 10.6, right? Minus 0.4 times the log area. Right? And then plus the 1.337 times this indicator for a fair. Right? So depending on the log of the area and whether or not it has the fair, you get this extra increase in the estimated log census population size depending on that. Right? So these different things, here's the F statistic, right, for testing whether there's a significant effect or not. Right? There were 2 predictors, so we get 2 degrees of freedom. There are 93 counties, so 90 minus, so P is 1, 2, should that be N minus P, 2, 1, 2, P is 3, right? P is 3, P minus 1 is my 2 predictors, X1, X2, right? So it's all, whether it's, some books will put P as the number, some will put P minus 1, but anyway. So this is right, there's 2 predictors, and then there's 3 coefficients, so 93 minus 3 is that, right? So the p-value for testing, is there any relationship, is very small. Right? Now, testing is the coefficient for log area, is that statistically significant? Well, it's still not quite statistically significant. There's the estimate, a standard error estimate, a t-value, that would be compared to a t-distribution with 90 degrees of freedom, and that's not too unusual, right? Twice the area beyond negative 1.685 is 9.5%. So it's not quite statistically significant. The testing for the fair, though, right, that is highly statistically significant. That fair does seem to make a difference. Right? So we can try to illustrate what's going on in that picture. I'll have to make that bigger to see it. So I'm going to save that. Maybe I need to attach. Did I attach Nebraska? Make sure that's there. The summary. You can do confidence intervals for each of those, but we'll come back and do that. So if I save that and do a plot of the data, Now if I can pull off the coefficients from the model, the intercept and the two slopes. So the first one is the intercept, and the second one is the slope, right? And that would be when there is no fare, right? So if the fare variable is 0, that goes away, and that we just get the one line. So the red one is the one without a fare. And so it's going down with log area. The one with the coefficient, with the fare, the third value here gets added on to the intercept because of that it's an indicator. So you can plot that one's going to be blue. So just run that one. There's the other line. Right? They're parallel. And this distance, this 1.4, is the distance of the 1.36. Is that amount of the fare. So we could try to do a plot to show that a little bit better. Right? So if you plot the area and say that PTH is that fare, right? Try to make this a little bit smaller and see what it looks like. True or false? Oh no, I didn't do that. It can't be quotes. Right, so maybe you don't need to make it smaller. Get the regular size, right? So the squares are one type of thing, right? And then the circles are the ones that do have the fare, right? The circles have the fares and the squares don't. So when we put those lines on there, there's the ones that don't have the fares, right? And it's kind of going along with the squares there. And then the blue ones for the ones that do have fares, right, are kind of higher. So it looks like the ones with higher population are able to afford or put on a fare, whereas the ones that have smaller populations look like they can't, right? Eventually we're going to look at residual plots as well. Here's the fitted values, the estimations, and these are the residuals. This is what it kind of looks for this data set. Right? There is some pattern in the X's and the fitted in terms of size, that there's some more moderate population sizes and some smaller ones, and one looks really small. Right? That's fine, that doesn't really violate the assumptions. We kind of want to look in the kind of bins here going up and down. Is the spread up and down kind of normal-ish distributed? Right? Is it kind of the same? Maybe there's bigger variance coming here as you're going along, so maybe there's a class of medium counties or small with a smaller one, and then these. Maybe there's kind of a break point where you get a bigger city and get a bigger population, but then there's others that just don't have anything like that. Right? If we do analysis of variance, it actually gives us a line for each predictor, right? And that's not how we usually look at it. We will talk about this kind of breaking out, this partitioning of that. If you do, where is that, my last? To get one like we think, I don't, oh. Something just got cut off. Let me put that back. This ANOVA command, you can compare maybe I want this one. Oh, that was right, sorry. It was there, I just didn't see it. This one, this thing here, so here's one model, right? That model doesn't have any X's. It just has an intercept. So this one there means here's just a model with an intercept, right? And here's a model with two predictors. So kind of stacking the ANOVAs there, it will take the difference of those two and give us the ANOVA table that we want. Right? So if we run all of that, we'll get something that looks like this. It's kind of an upside down ANOVA. We'll go back over this, but this ends up being the model, sum of squares, the regression sum of squares, the residuals. It creates an F statistic and gives this test. Is there any effect of these? But we will go back over that. Right? I wanted to see if things, what happened with the density variable. Now it looks like if you have the density variable and the fare, you can get two things that are statistically significant. So density seems to be a better predictor than just log area. It seems to capture more of what's going on. So anyway, that's kind of a brief introduction to what you can, some of the things you can do, a little look at some of the coding, right? And then next, so on Wednesday, we'll look more at things in a little more detail, kind of step by step through some of the models. Have a good break and see you next week.
Thank you.
Bye.
Thank you.
Yep. Yeah. Faye, you know. You're looking at something for schedule or?
Just the homework 5.
Uh-huh.
We started yesterday, right?
Oh, okay.
So, by myself.
So in the simple regression, you could do a confidence interval for the slope or talk about the hypothesis test for a slope. Either one is fine. Save this briefly.
So, write a short report for each question,
So yeah, right.
everything you mentioned here.
Yeah, or what kind of seems relevant for it. I mean, if you don't have everything, we just kind of put together a nice little, so look at the data set, think about estimating the model, and sometimes is there an outlier or is there a transformation, and then kind of maybe show a graph or two, do a statement that has an inference for a parameter, a prediction, and then kind of include. Each one I wouldn't imagine being more than a page that they, right, so the questions that they ask in the book are pretty short, right, and just kind of, run the regression. It's like, well, maybe you'd like to say a little bit more. So just short descriptions, short answers, but to kind of do what you would do a useful kind of summary. So, okay, yep.